So, hello everyone. I hope the sound is good. Otherwise, you can write in the comment section. You can write in the Q&A if you want to contact us in any way. So, welcome to today's webinar. My name is Niels Petersen. Normally, I work with rain erosion for R&D Test Systems. Today, I'll be mediating this talk. I'm not the absolute expert in this, but we have invited 3 people who are. Rain erosion is a challenge that keep causing headaches all around the wind turbine industry. And even though I've worked with this for many years now, it still puzzles me all the details and minor reflections of this challenge. Today we're talking about rain erosion in general terms. So what are the consequences? How are protective systems for leading edges developed? How are they tested? And what do we expect from the future? So we'll be talking for around 45 minutes. And after that, we have 15 minutes or so for Q&A. If you do have any questions popping up when we talk or afterwards, you can write it in the Q&A section. The commenting section will be closed. So we have invited 3 people today to share their insight. We cover both research, industry, and test machine design. And common for all of them is that they are absolute experts in rain erosion. First of all, we have Nina Schurman. She's a chemical engineer with Hempel and responsible for LEP development. Hempel is developing all protective coatings for wind turbines. Then we have Nikolaj Frost Jensen Johansen, a development engineer at the Department of Wind and Energy Systems at DTU. DTU is one of the leading research institutions in rain erosion testing. And last but not least, we have my colleague, Christian Emil Helver, who's a systems engineer with R&D Test Systems. He's an expert in test and verification methods of rain erosion. We have a lot of attendees today and still counting, so welcome to all of you. I want to kick it off a little bit with an introduction to the challenge. So Nikolaj, perhaps you could explain a little bit about what is the challenge. Could you give us a general overview of consequences?
Yes. Yeah. So as you say, like on the surface of it, rain erosion is both. It's a complicated problem to tackle, but at the core of it is, deceptively simple. It is, of course, the problem we face on all leading edges. Now we are mostly focusing on wind turbines, as it's the leading edge that probably sees the most flight hours in a year, and it definitely hits the most rain. And of course, at its core, we know the driving factor in leading edge erosion, rain erosion, is impacts with rain droplets. So at the very highest level, of course, it's a process where we impact hundreds and millions of rain droplets over time. They're each impacting with a fairly high impact pressure, and it drives what on the surface of it looks like a fatigue process. That is the ideal case, maybe not always the case. And it's sort of like, what are the main drivers of erosion? Like sometimes you hear, is it worse onshore? Is it offshore? UV, whatever. I think all of them are potentially impacting factors, but I would say the main thing to really grasp with rain erosion is really the amount of rain that we see and hit on a wind turbine. And just to sort of put some numbers on, and also to understand a little bit the situation of it is, let's take a general place in Denmark. That's what I tried to illustrate on this figure. Maybe you get about 700 millimeters of rain, so 0.7 meters of rain. So that's what you measure on the ground, but that's not what a wind turbine sees. So as rain is falling, there's rain in the air, and it comes down to that question: should you run or should you stand still in the rain to get the least amount of rain? That sort of depends on where you want to get wet. But for a wind turbine, let's imagine we take the same bucket that stands on the ground, we put it on the blade. Now this tip of the blade is rotating at about 324 kilometers an hour. We have a 90-meter-second turbine, and that spins around in our rain. Over that same year, that bucket would collect 10.5 meters of rain. That's what we term impingement. And when we look across most factors that really influence rain erosion, it is this amount of impingement that a turbine sees that's the first factor that starts influencing that, and then of course the velocity, and it's one of the things where we can see also differences where the metrology has to go in, because this is really complicated at times to calculate how much rain actually hits a wind turbine. If you were in Denmark yesterday, you would see all these showers that came in, and some of them last like seconds. So you really need really high fidelity metrology, really good material models, and everything has to come together. And of course that all have to play together, and we get our models, and of course the influences and the consequences, as you say, is that one is it's a degradation of the surface, and either that influences that you need to repair at some point. I think that's for a large part the main motivator in doing it, because repair campaigns are costly. So as we look into, we can run these tests and we see different types of failures. We look at, on the research side, we're very focused on incubation. So we talk about the very first damages that occur. That's of course quite far removed from something you would repair in real life, but that's the best metric we have for sort of finding the early parts. And of course the consequences when erosion has progressed maybe a little bit more, like the picture down in the corner, going down to the substrate, we start also seeing that AP is a factor in how it influences turbines. Like there's been a lot of numbers on what the AP loss is. When we looked at old stall governed turbine, maybe it was all the way up to 25%. I think we're now fairly sure it's not that high. At the biggest, the numbers now on AP seems to have converged about the worst case as like 1.5%, and then sort of constantly like, okay, 1.5% is not the biggest number you've ever seen, but of course, at the scale and in magnitudes of energy that a turbine makes, 1.5% is very severe. But what's really tricky in it is, all the best science we've done is like with scatter data from a turbine, it's basically impossible to tell if you are operating with erosion. So you have to a little bit trust that the science, you do lose power, but it's I think the best sort of analogy I have for it is like you're out on a hike and you have a big backpack on, and the guy behind you is a bit of an asshole, and he keeps dropping a pebble in your back. And of course your back is getting heavier and you're doing more work, but you can never tell exactly when was it your backpack got heavier. And that's sort of the problem with actually sort of measuring the direct consequence on the blades. It's like we know it works and it has an effect, but it's really hard to put on the turbine to see. So it becomes a lot of trust, and that's also, I think, a lot of people in the industry feels there's a lot of snake oil being peddled in rain erosion, that you're losing so many percent by our magical solution to solve it. And I think that's really what we want to try and cut through the bullshit, so to say, and actually put the science behind it. Yeah.
Great. Thanks, Nikolaj. I was wondering, do you differentiate the challenge between onshore and offshore? Is there any differences in terms of the consequences or how severe the impact from rain erosion is?
I think we see two main differences when we look onshore and offshore. And the first and foremost, I would say it's a matter of cost and risk. Like the severe risk of an offshore situation is like, let's say you have a failure early on in the season to a degree where you would have to curtail a turbine. Like that's the worst case scenario, and that's millions of euros. So on that hand, then you tend to want to invest in better solution. But we have also seen more severe erosion offshore. And I think to that explanation, from where we've analyzed it, there's two main factors. We talked about this amount of rain a wind turbine hits, and that sort of combination with offshore turbines typically have a higher capacity factor, so meaning they're running at full speed more of the time. And then it comes down to the metrology. Often when we look at how rain is offshore versus onshore, you can take two sites that gets about the same amount of rain, But more often when it rains offshore, it's also windy. Whereas when onshore, you get what I've learned now is called convective rain, where rain just more drops straight down and it's not necessarily associated with a lot of wind. So we really need to, at that point, go in and see, okay, what is the turbine doing when it's raining? And when we account for those two things, many of those questions, okay, yeah, I can see from this, we're attempting some rain erosion atlases, it becomes quite clear that a lot of the offshore sites, purely based on the metrology, is just much more severe for wind turbines. Then, of course, there's other environmental factors that may or may not play in. But I think the first part is really to recognize that the metrology of an offshore site is really different.
Thanks, Nikolai. Good overview. I want to move on a little bit now to the industry actually tackling this problem. There's a lot of companies out there working to make protective materials for the leading edges, and one of them is Hempel. So, Nina, I'm wondering how Hempel is approaching developing a leading edge protective material. What do you have to consider? What is kind of your target?
Thank you very much. So the first coating that Hempel launched for wind turbine blades in 2022 is Hempel Blade Edge 171. And here you see an overview on the wind turbine. So since then, Hempel has launched a full coating system. And in the end, it's the full coating system that together has to provide the protection. The leading edge protection goes specifically on the leading edge, the area of the highest impact on the wind turbine blade, and thereby, of course, has the major impact on the erosion protection, but all layers work together as such. So since then, Hempel has launched a full system consisting not only of the leading edge protection, but also of putty for the leading and trailing edge to shape the blade. Pore filler, in case there's any surface imperfection, can be used to correct those. And that's a very important part because any defects can cause an earlier erosion. So defect-free application is a big consideration here. And then followed by final 151 and final 161, which are our top coat solutions. The first one is a waterborne solution. The second one is solvent-borne high solid solution, which protect the whole blade. And then, of course, followed by the leading edge protection solution, of which we have 2 on offer right now. So I was already mentioning that the whole system has to work together, and the performance in rain erosion was a key consideration from the very beginning of the development of the all these coatings. All layers were tested individually and also together as a full system, where the in-house capability of a rain erosion tester was a key for the development. By now we have run more than 1,000 test sessions, really, to confirm all kinds of things, each individual layer, the full system. Majority, of course, goes into the LEP development. We also look at what kind of consumables to use, what kind of impact climate conditions might have, and so forth. So we use this rain erosion tester to verify not only the erosion performance, but also the adhesion of the layers between each other. So that could be that we can recommend to a customer what is the ideal surface preparation, for example. And the rain erosion tester itself, with its severe erosion environment, is one of the most severe tests we can do for intercoat adhesion. So we've used the machine in all stages of development, from screening to our final prototypes, up to qualification with customers, as well as quality assurance when we talk about scale-up production and so forth, so we can ensure that each batch fulfills our requirements for performance. And if we look at paint considerations, then of course there are a lot of considerations to take. So how should the wet paint be? How is the leveling, how high of a film thickness do I want? Our putty, for example, can be applied up to 1 centimeter thick, while that, of course, for a top coat is not really feasible. So we target different kinds of properties with our different layers. We look at different mechanical properties. So the LEP, for example, is a very strong material, at the same time extremely flexible, so that it can dampen the impact of the rain and particles that impact the leading edge. Important considerations are also application methods, what kind of delivery form is convenient for the customer. So leading edge protection, for example, goes on a very small part of the blade. It doesn't make sense to deliver it in 200-liter drums. So instead, we deliver it in small cartridges, which are easy to use for a customer. And then, of course, health and safety regulations, as it's people working with the products and blades are extremely big shapes. It's a big consideration for us as well to minimize health and safety impact for the people working with it.
Thanks, Nina. I was wondering, you're talking about the actual application process. Is it possible to quantify by any means the importance of the application versus the importance of a durable top coating system?
I would say the application is extremely important because especially what we see with modern state-of-the-art leading-edge protection materials is that defects might limit material performance more than the actual material properties do. So any kind of air bubble is like a stress in the coating and could lead to earlier erosion. So an easy and reliable application is a key. We want to minimize defects as much as possible and make the application as easy as possible so one can achieve good results in erosion.
Is this system both for OEM purposes and retrofit purposes?
Yes, it's for both. I mean, some of these layers are specifically targeted for OEM purposes, like the putty in this case, for example, is less suitable for maintenance and repair in terms of how it's delivered. But yes, the coatings, we have different points, for example, with our leading edge protection coatings. Edge 172 is a one-layer system with a bit higher film thickness compared to Edge 171. That makes 172 a bit more targeted towards maintenance and repair, for example. But yes, we have coatings that can be used for both solutions, for both application methods.
Thanks a lot, Nina. So we have heard now a little bit about the test machine, and it's no secret that all three of the experts we invited today operates their own rain erosion tester. Christian Emil, could you tell us a little bit about how you actually test performance of LEP systems?
Yes, of course. Yeah, as both Nikolai and Nina mentioned, they've been doing some rain erosion tests on the rain erosion testers when they are developing new leading edge protection systems or when they are developing new concepts. And these rain erosion testers were built by R&D Test Systems, the team that I am currently working with. And I'm actually joining in from South Korea today, where we just finished commissioning our 17th machine in the line. So when we are working with testing systems, we want to develop them to be representative of the actual application, and we want the results to be reproducible so we can get good, consistent results between the different tests, so we can get a fair comparison between the LEPs that we're developing. And in the industry right now, we have two kind of prevalent technologies. We have the pulse jet testers and we have the whirling arm testers. The pulse jet testers, they work by shooting a high stream of a high velocity stream of water at a stationary target, and then interrupting the stream so you get this pulse jet that hits the target, where the target is of course the LEP or the test specimen that we are doing testing on. And it has a very high energy per impact, but so we can accelerate the test, but it doesn't offer very good material properties in regards to the representativity. And this is of course because the water droplets that are hitting are not actually water shaped, it's more of like a jet, and because the target, the LEP, is stationary, and so it doesn't get an aerodynamic response through the test. Whirling arm testers, on the other hand, you can see an example of a whirling arm tester to the left here, the left picture. They create a rain field and then they spin a test specimen throughout the rain field. And in this case, the rain erosion tester from R&D Test Systems, we create this rain field through 600 to 1800 needles, as you can see in the top here, where each needle is continuously dropping droplets of water down, so we create this artificial rain field. And then we are spinning the test specimens on the rotor in the middle, where you can see this helicopter-like principle where we have 3 blades sticking out, each with a long specimen mounted to it. So this kind of design allows us to get some radial speed variation of the test specimens, because the tip of the specimen is, of course, moving much faster than the root of the specimen, and this means that we can actually test at different speeds during just one test. So we will of course see the breakthrough or the erosion happen at the tip first, and then move along the edge as it needs less number of impacts to break through at high speed. This kind of design also offers us a good test parameter control, so we can get a representative system compared to the actual applications in the industry, because we have a lot of different parameters that we can play around with to get conditions that look as much like the industry as possible. And here we can, for example, choose the droplet size by choosing these needles that we have in the top. We can choose the water flow, or how much water is hitting the system. As Nikolai talked about, this is very important, the water impingement. We can control the rotor speed. We can go up to 1800 RPM, which gives us a tip speed of about 235 meters per second, which is much more than we see in actual applications today. But we can, of course, control the velocity so we can get a lower speed if we need to. And we also want to accelerate the test and be future-proof with higher speeds. And we can also control the temperature of the water and the test chamber, so we can try to emulate reality. And of course, many more parameters, such as like how long we are testing, how many pictures we're taking, how long standstill we have, and all that kind of stuff. After we've done a test, we want to inspect the results, and we want to evaluate how good they're doing. And in the industry, they're currently using many different kind of methods to do this. We of course have visual inspection. As you can see on the right picture here, we can go out and see how the system erodes, or how the erosion happens during the test. We have a camera mounted in the inside that can take pictures throughout the test, so we can see how the erosion progresses through the test. We can also do material loss tracking, so we can weigh the system or the specimen before and after and even during the test to see how much mass we're losing during the tests. And some of our customers are even doing 3D surface scans of the system to see how the water droplets impact their LEP systems. And all of this adds up to a system that we can modify to be representative of the actual conditions of the actual wind turbines. And we can, of course, never get like really exactly the same results as is in a lab, but we can make as representative as we can do it in a laboratory environment. And thereby we can also get very reproducible results, such that Nikolai and Nina and all of our other customers can accurately compare the different kind of LEPs they are measuring and evaluate their performance during the test.
Thanks a lot, Christian Emil. I was wondering, in terms of the repeatability, which is quite high for the machine, what is the main challenges you have seen to achieve high repeatability on a single machine, but also from machine to machine? Is there any difference?
Yeah, there's a lot of, we actually just did a study of this where we compared, or we didn't, I think Nikolai was a part of it. There was a study done on our machines where they compared 3 of our testers, and we got a coefficient of variance less than 20%, where one of the machines were a little bit different than the others. And we think this is probably due to the water quality. We have a lot of systems that want to add minerals or like to get the water to a consistent level. But the water you put into the system is, of course, still a factor. And if that's a little bit outside of the limits where we put into it, then we can get some different results. And also we have a lot of needles, as you can see in this picture. We can get up to 1,800 needles if you choose the dual rain fields. And the needles, of course, can create point erosion if they are not staggered correctly from each other. So we need to get like a completely as stochastic as we can droplet distribution. And if one of these are like moved or something, then we can see that the water distribution is not completely accurate, and we can see like this point erosion that we're working a lot with.
Thanks a lot. Nikolai, you are also operating a machine, one of the newest machine in the fleet. Can you tell us a little bit about the limiting factors or the challenges in testing? I guess it's not only sunshine and good stories.
No, of course not. I was wondering if I was allowed to use this picture. Yes. So the short one is, of course, it's our tester, our big box, and the box is the main task of the rain erosion tester is to be, as the blue box, a time machine. Unfortunately, only travels forward in time, and it is exactly the same size on the inside as it is outside. So it's a little bit disappointing, but I will deal with that. But of course, like we at D2 decided that like in the rain. We've been in the field of rain erosion since 2016 through various projects, and there we've been fortunate enough to have access to different rain erosion testers, various versions of the ones at R&D before they get skipped out to somewhere else, but also the industry testers. And we were fortunate enough to do some studies. One of our good publications is the drop size study, where we looked at various droplet sizes. And one of the things that we really then narrowed in on is, it's clear that the industry needs these testers because the tests are so long. It's hard to go to a commercial operator since there's very few of them on the market of running purely commercial. We will also be providing a bit of commercial testing capacity to the market. But again, the time it takes to run a test is really, in many cases, the limiting factor if you can even afford to go commercial. And one of the motivations we found, and we wanted to look, how can we accelerate the test more, but still keep it physical? And the standard test, as you say, either it comes with 600 needles, you have the expanded rain field of 1200, and then you combine them to 1800. And the motivation on that is that we think if we look at how it's progressing, it seems we can linearly scale the erosion time with the amount of impingement the blade sees per second. So if you can add in more water into your rain erosion test, right now there might be a limit on where it becomes unphysical. Right now it seems to scale quite linearly. It's one of the things we want to look into. If you can see my tester behind me, it's a little bit different than Christian Wiens, and that's because we have the dual rain field. Where we can, again, add in the more rain. And it also then ties back to the metrology because, right now the rain erosion testers are running typically with about a 2.4 millimeter droplet. That's semi-arbitrarily chosen. Like the old standard just say 2 millimeters. If you ask a metrologist, it's apparently way, way too big. So it's also one of the design parameters we wanted to say, okay, it doesn't make sense for the industry to play around with all these things. It's non-standard. And there were no R&D testers within a pure university environment. So it also is really tricky for the industry to go in and play with any of these parameters. So that was the motivation when we just spec'd out what our machine could do. Okay, we need to be able to make as much different rain as possible, put in find where are the limits of acceleration that we can go. Also, I think a new feature that gave a bit of headache to get running, but now it's really good. Also, that we have added more temperature control both in the air and the water, because again, as Nina says, these are really soft coatings, and the downside of soft coatings is also that their viscoelastic properties, so their sort of stiffness, can also in many cases change quite drastically over just a short operating temperature. And in many cases, maybe it doesn't matter, but maybe there's somewhere it does, where if you're testing for a northern winter climate or a southern monsoon climate, are your material be performing the same? And those are some of the fundamental questions we really want to answer. So that's been the big driver behind them designing things in our tester. I think the only thing we didn't go for was the aerospace upgrade, because like we're mainly focused on wind turbines. Maybe some point in the future we want to go there. But yeah, that's really the and also on the practical levels, it's old coatings. Like it's clear since we started looking at coatings back in 16 and where we are now, they are an order of magnitude better. But the problem is an order of magnitude has moved up from 1 year of lifetime in some cases to 10 years of lifetime. So we still have quite a long way to go. And to be honest, if you use the standard rain erosion tester, it's not accelerated enough. If you follow how the standard says that we should test, some testing at 160 and 100 meters a second, with how the most of the 17 reds are configured, it could take you on the other side of 1,600 hours of continuous testing, and maybe you get one data point, because that's also the second consequence we've seen. As better the coatings have become, the less data points we're getting from testing. So if theoretically, and that's what we haven't confirmed it yet. Sort of what we was designed the machine as that we could push 6 times the water flow in, which should give a 6-fold reduction in testing time. Theoretically, again, that is still unproven. We need to see how far we can push that, and that's one direction to cut down this time and get closer to, because the goal would be like we want coatings that should last the lifetime of the turbine, 30 plus years with no maintenance. I don't think we're quite there yet, but I think at some point we will be. But then we also need testing that can give us trust in that, like what this time machine tells is true also when we go those 30 years ahead. And then of course we need to add on top aging, weathering, all these things that then on top of it. But at minimum, the tester should within a realistic time be able to give us that load. And we're still a little bit off, but I think we can get there.
One of the key differences from the tester versus the real life is also the shape of the specimen, the actual geometry. Relatively seen, the surface of a real leading edge would be more flat compared to the specimens you're using. Do you know if that makes any difference to the test result, Nikolai?
It is something we're looking into. We have a student right now also trying to model some of these effects. So the nose radius on the rain erosion specimen is quite sharp, and is relatively small and moving. So the stagnation zone, or sort of the area in front of dampened air, is not extending as far forward. And one of the things, there are some publications, I think Niels Bachneck did a really good publication on as well, that a real turbine has a bigger radius, so that stagnation zone of sort of slow air in front extends a bit further and has a bit of more time to slow down a droplet. And now we didn't show any VN curves today, but the real tricky part is that it's a really strong power curve on which we model rain erosion performance, meaning that if you're on the right part of the curve, moving just 1 or 2 meters a second could be the difference from 10 years of lifetime to 1 year of lifetime. So there's an added effect that could actually slow the droplet down a little bit before it hits the blade, and you get another result. This impingement efficiency, and can also maybe explain why sometimes smaller droplets would be less damaging the bigger droplet, because a small droplet is more likely to get carried by the airstream than the bigger droplet that just bulldozes through that stagnation zone. So that's it's still a little bit unclear. We're the first sort of attempts on this aerodynamics have been being done as we're speaking. But yeah, that's the short of it.
That's really, really interesting. I think we should move on from a research perspective to a more industry-like perspective in terms of testing. I assume, Nina, you have a different approach to designing test campaigns, testing, etc. Maybe also evaluating. Could you walk us through how the Hempel approach to testing in terms of validating, development, and so on is done?
Yes, of course. I mean, some things Nikolai already touched upon, like, for example, the possibility of changing the needles, changing the droplet sizes. It's something that we are a bit more limited simply in terms of time that we have, and also the possibility of the dual rain field, which is something that our tester itself not has. So that's something where we limit ourselves to one droplet size. However, maybe let's look at a whole project, like when we would develop leading edge protection coating, what kind of considerations go into the testing there? And they depend largely on at which stage of the project we are. So that goes all the way from the very first idea, what a product should look like in the end. So what kind of challenge for the customer do we want to solve? Like, is it for maintenance and repair? Is it for OEM? How big should it be, etc. On to the very final product. So at first we would screen possible materials, check, select the most suitable ones based on some mechanical testing first, simply because it's a bit faster and also cheaper than operating the rain erosion test. But with the most promising candidates, we would do some rain erosion testing to get an idea on the performance. And at this stage, we want fast results because we want to see if it works. We want to see if it works fast. We also want to see if it doesn't work very fast. So we could use high-speed testing, 160 meters per second, for example, of tip speed. That's 570-ish kilometers per hour, simply to reach fast results. That's highly accelerated over the tip speed of a modern turbine. But then as we move closer to the final prototype, so first we do feasibility studies. Okay, can we reach what our idea looks like? On to prototypes that might not fulfill all criteria, but most of them, all the way to the final product, production and quality assurance. So a first prototype that meets the product profile that we have set ourselves, like drying time, pot life, the adhesion properties, and will undergo basic performance testing, also at few lower speeds, so we get an idea about performance at different speeds. However, as Nikolai said, testing at, for example, 100 meters per second at this stage is not yet feasible because it would take a very long time. And at this stage, we want to move on a bit faster. So all that testing would be undergone in standard conditions, like application in a standard controlled environment, some first compatibility tests to existing products that we already have in the market, etc. All the way to the final prototype. And with this final prototype undergoes a lot of long-term testing as well. Application and curing in various climate conditions, back to operation testing where we check how fast we can expose our material again without achieving cold flow or other disturbance of the surface. Accelerated aging and weathering, where we expose the applied rain erosion panels to UV light, to salt spray, or to cold temperature, freezing temperatures, and see how they look after aging. Compatibility, surface preparation methods, and also consumables that we want to recommend, like which roller, which brush to use, or the settings of the spray guns, of course. And the paint itself at this stage also undergoes stability testing at different temperatures, as well as scale up in the production, of course, since we can have the best paint in the laboratory. In the end, we cannot send it to our customers if we cannot scale up and produce a significant amount of it. So these production trials undergo quality control then again, where we again set a standard target for performance that the coating has to reach. That could be this VN curve that the coating has to reach, or a certain incubation time, meaning the first time when we see erosion. And and then in the end, we have a product of which we are confident in its performance. And then together with customers, you would undergo their qualification process. So a customer might rely on some of the results that we have already generated during the project. At the same time, they might ask us to do some additional testing, which we can then provide, of course. And for any kind of other situations, when customers ask us specific things, of course, then we would go over to the support phase, away from the launch product towards the support phase, and supporting any customer needs. Oh, can I use this brush? Can I don't know, apply in these conditions? Big scale testing, big scale application testing, etc.
That's a really interesting perspective and important perspective. We are running a little bit out of time. Remember, if you do have any important questions, then write them in the Q&A section, and we'll try to address them in the end. My last question, and that would be to all of you, is regarding the future. What does the near future hold for your different perspective? What do you expect from the far future? Let's start with you, Christian Emil.
Yeah, on the test machine side, I think in the far future, we want to look into how we can accelerate it even further, as Nikolai says, how we can keep up with the demands from the industry. And it sounds like with the studies he's been doing, that we can do this through just more water impingement, so maybe adding more water or something like that. But we are continuously looking to upgrade these machines and be on top of the studies and how it's done in the industry. On the more short-term side, currently we're actually upgrading some of the older machines to get them up to the newest features and all the bug fixes we've done, get them up to a new software, and even get maybe some of hardware upgrades to some of the systems. And we're also working on developing a few different features that we support on this new software. For example, we just went to a very interesting symposium at DTU, which was held by DTU and Nikolai. And a lot of very good subjects were brought up. And one of them were the rest periods, that you can actually extend the lifetime of an LEP by up to 6 times by implementing resting periods where they don't experience erosion or don't experience any water on them. And this was actually really interesting, because if we have something that can increase the point of break or point of failure by 6 times that we are not taking into account in our system, then we of course need to get that implemented. So we're looking into right now actually adding some rest periods, like some controlled rest periods into our system, so we can control how long it stands still. And we're also developing a new tester, the one you can see here in the pictures, the Rain Erosion Tester Compact, which is a simplified alternative to the big testing machine. It only have the most essential requirements, so it doesn't have like the full customization options that the big machine has, but it's more affordable, and it can give a lot of new customers a way to get into the testing market without having to buy the full option of it. And I think Nikolai, he talked about his system before, that they have all of the different options We actually called that the Rolls-Royce model because it had like everything, all of the nice features. And then this compact version here, it would be like a more sensible Hyundai version, I think. So yeah, you saw in the picture before here how we moderated our own testing chamber to test the smaller size of the rain erosion tester. So yeah, that'll be our new big project to get this the compact version up and running.
Exciting me. I'm happy that there's a rain erosion tester for everyone out there.
Yes.
If anybody is truly looking into the future, I guess it would be you, Nikolai. In terms of research, what are you looking into now? What are your expectations for the future?
That's so we've talked about the added rain. That's sort of the most upfront. We need to look into this to see, like, does the hypothesis hold that we can accelerate the test even further? And from our point, it's both motivated on reducing the testing time. For if we're doing research, then maybe we're not that concerned about it. But especially we see now that we're also providing this as a service to the industry. And it is a costly test. There's no way of getting around it. And the more erosion we can give per day of testing to the customer, that's a clear benefit. Also for anyone that wants to dip their toes in rain erosion and maybe are not ready to buy a compact model yet. So that's on a lower level. And of course, we need to understand we're pushing the limits of feasibility. I think the next part that's really going to be interesting for us, and we'll move into a bit of a different way of viewing how failures happen in rain erosion. So right now we've assumed that everything is progressive from the tip to the root, but as Nina said, like, it seems very defect sensitive now, and that's also what we see. A coating can look perfect, and then you have like one random point where it fails. And we want to understand this randomness and why there are some coatings that are for some reason better. And you sometimes hear it in the industry that this magical coating, you can brush it on terribly and it looks like shit, but somehow it holds. And we've also had coatings that looked a little bit like shit, and for some reason they held. And what we will look into is it's moving a little bit away about this async approach where that's very empirical. You just see after an amount of time it fails, and for the most part, sometimes it does follow a curve, but sometimes it doesn't. But something that we're expert in this section is fracture mechanics. So we want to dive into, like, erosion is a process as a crack and it grows. And there's various ways that we now want to characterize, like, how does these soft materials, can we find a stress value where a crack doesn't grow? We want to find which material parameters actually govern this crack growth rate, and can we find a threshold value? So design coatings that are, there's a threshold, and if there is a crack, it shouldn't grow. So then you have a coating that's resistant to a defect. And that's where our hope is for coatings that really truly last the lifetime of a turbine and are resistant to the defects that are inherent in any paint application or whatever. We really truly believe there is a solution to this, but this will require us we're making an entirely new way of doing fracture testing in very soft materials. It's super tricky, and getting projects where we can compare that from the lab to the rain erosion tester, and hopefully at some point tying it all the way to the field. That's on the material side, the big hope, and that will be a very different way of viewing the material performance of a rain erosion.
Very interesting. I'm looking forward to follow the research in the coming years. You mentioned material lasting a turbine lifetime. Nina, is that feasible now or in the future?
Well, I hope that it will be in the future. We see that constantly the performance of coatings is increasing. And of course, as a coating manufacturer here, we also try to stay up to date with the research around rain erosion, do some research ourselves where the R&D capability in-house also helps us to validate some hypotheses that we have in terms of performance. Yes, so I hope so. I hope so for sure. And as such, of course, we want to also look at these defects. Defect tolerance of coatings is one of the big topics, because I guess when the blade is about 100 meters long, we have to acknowledge that at some point there might be a defect that that could be there, that could be overlooked. And as such, it's something we are also looking into. Of course, we also look at our machine, having it up to date, as you mentioned, upgrades, etc., is something we consider. We see that high-speed testing increases further. It's something we are also looking into as the performance of coatings simply increases a lot with more and more performing materials.
Great. That was all the questions I had. We do have a couple of questions from the audience. First of all, Nikolai, I want to ask you your opinion on using computer vision or AI to analyze the photos from the testing, so the results.
I think it's really a direction that we are pushing towards. But one of the things that are really tricky, and we showed a little bit earlier, mainly when we're looking for incubation, which is the main thing we can identify reliably. These are extremely small, and it's almost down to the pixel noise in the systems. So that has been challenging, and also just good annotation tools. Like it seems simple, hard, but even the first point of just having the tool where you can click a point on the image and keep track of all your damages has been really tricky. So now we've spent a couple of years now getting our own sort of more research-orientated tool up and running, and I really hope we get some opportunity now to get enough training data to get some AIs to do it, because this is truly the worst part of rain erosion testing, is to sit there for a day and click 1,000 pictures and find small fly specks on your blades and separate it out. But it's really where you can extract a lot more knowledge out of the data. Like some of the things we're doing now is trying to track when a pinhole occurs, for example, how quick does the damage grow? So we can mark up the area of every slice. And like some of the funny things we saw, like we looked at the coding, it showed pinholes quite early on. So if we judged on that, it would only be like a 3-5 year lifetime coding. But then we looked at those damages, how quick they actually grew. And so there was a long period of just growing linearly, but very slowly. There might be some calculation area, but our estimation was to grow to 1 square centimeter would have taken 1,000 years. So, that could have been a coding that you discarded because for some reason it gets a lot of pinholes that show up very early. But if those don't grow, then is it a problem? I think that's the part where we're wanting to move into, and clearly for that area growth rate tracking, we need to go into some AI, because you can only get master students to do that for half a year and then they go away. And I don't want to sit there and paint every small damage.
This is actually something that we have been looking into a little bit as well. And how do we make the, as you say, Nikolai, how do we make this our annotation systems AI ready? And because one of the big challenges in implementing AI is, of course, feeding it a big enough data set that we can train the AI on it. And for this, we need some requirements, like, for example, we need to make the erosion pattern highlighted in red or something, for example, so the AI is has an easier time recognizing the patterns. So this is something that we've been talking a little bit about as well, and maybe see a future in as well from R&D side.
I'm happy that there's still a lot of room for development and getting more data, getting more results, and getting better results. We have a question to Nina in terms of the LEP performance and how to achieve the best performance. So from your take, Nina, after extreme flexibility, then what is the most important aspect in terms of the LEP performance?
Well, from a material property standpoint, we could, of course, say, okay, a low glass transition temperature and the flexibility that comes along with it. It's damping properties, it's defect tolerance, so the fracture mechanics of the material, as Nikolai already mentioned, is something that we look at. But from a coating standpoint, I'd have to say it's probably adhesion, because if the coating doesn't stick to the surface below, then in the end it won't provide the erosion resistance that we desire. So that's a big focus, to have a coating that sticks to various surfaces that we face, and especially in maintenance and repair situations, we do not only have our own coatings, but previous coatings, aged coatings, maybe a slightly dirty surface that is prepared as best as possible, but it's still prepared by people hanging on a rope in like 70, 80 meters in the air. So that is one of the big considerations, I would say, from my side as well, beyond the mechanical properties of the material.
Thanks a lot. A general question, one that I also get asked a lot, is what about other types of erosion? Could be sand erosion, dust erosion, hail erosion. Very briefly, Nikolai, is this a challenge that you have on the radar?
Yeah, for sure, and it does come up in many cases. Of course, there are limitations to what we can do. Before we had our rain erosion tester, we did a lot of. We have our SPIF that is basically shot rubber balls a little bit more, so we had solid projectiles hitting the materials, and we could sort of mimic the similar kind of failure over time and get sort of relatively correlating results. But of course, when it comes in hail, is always the big joker, like what does it do? And especially how do you determine what the impact of hail is? I think if you just do kinetic energy, which I don't really believe in is directly translatable, but then of course it's very severe because you can get some big hailstones. Again, the rain erosion tester is not an hail erosion tester, but we are working with some ideas that's one of the things. Our machine, we just build in more head height, so maybe at some point we figure out a way to drop some few hailstones in there and at least put on a high-speed camera and see what happens. One of I think what we're working with is maybe a big hail impact can be that initiator, that defect that cuts the coating locally and gives that initial crack where it starts growing from. That I think will be the first direction, like pure hail erosion, where you only just do a ton of hailstones and things that fit out in the future. And then of course, I think dust that maybe it goes more over to Nina and Hempel's side, but at least I can see it's a tricky part because a lot of the new LEPs are really, because we are so soft, I think they are maybe a little bit more sensitive to the fouling and sticking. I think we had one really good coatings that we accidentally made in the dual edge project, which is like it's cured but super sticky. And I think that lasts super well in rain erosion, but I guess it would be terrible in real life because everything would stick to it. It would probably accumulate half 100 kilograms of dust over a short amount of time. And I think for sand and particle erosions, there are some good blasting setups. I think if you're considering sand and dust erosion testing, you really need to focus in on machines that can really introduce a low impact rate of the solid particles. We did some years ago where we did some testing, and if you have your impact rate too high, your coating simply overheats and fails. Then you get completely opposite results, like a magnitude of difference wrong, where soft coatings fail within seconds and an old gel coat lasts half an hour if you get your impact rates too high. There are setups where you can do that. You just need to be really, really careful about impact rates when you talk about solid impacts, because these viscoelastic coatings, they take all the kinetic energy and make it directly into heat. And
thanks, David. I think I need to cut you off. Here we are running out of time. I want to thank you, Nikolai, Nina, Christian, Emil, for telling us about rain erosion, how it's tackled, what the future entails, and so on. Thanks for participating, everyone. After the webinar here, you will get a link to a recording of the webinar. You're always welcome to reach out if sudden questions pop up that you didn't get answered in this webinar. Thanks a lot for participating.